So a very, very important concept, especially in the case of neural networks, is the concept of transfer learning. So let me explain the idea of transfer learning first, and then we'll go into multiple cases on how to actually perform transfer learning. In the next video, we'll also see actually how to apply transfer learning to a real world problem, and we'll see code in Keras on how it is to be exactly done, right? We'll also see a real world example of transfer learning. First, let's understand the core concept and the idea behind it. The idea is this. Suppose you're given a task. Let's assume I'm given a task, and let's assume my task has a bunch of images of dogs and a bunch of images of cats. And I want to build a convolutional neural network, right, which distinguishes cats from dogs. So it's a two-class classifier, right? It's a two-class classification tasks. But I have images of dogs and cats, and hence I'm trying to build a convnet, right? In such a case, of course, I can build a convnet from scratch, right, to solve this task. The other idea is, instead of building, so the core idea is this: instead of building a neural network or a convolution neural network from scratch, right, to solve our task, what if we can reuse existing models. So we have studied a lot of models, right, like VGG16, AlexNet, etc. What if we can use an existing model architecture which is trained on a different data set? So for example, as I mentioned earlier to you in one of the videos where we learned how VGG16 works, Keras actually has VGG16, right, trained on, so it actually has VGG16 trained on ImageNet dataset. It already has the complete model trained, which means it actually has all of the kernels, right? In each of the levels, it has all the kernels, all the weights, everything pre-trained. So these are called pre-trained models. And these pre-trained models are available both in Keras and TensorFlow, right? And these models are trained on ImageNet dataset, which is one of the largest datasets for object classification. You're trying to achieve an object classification task. So the core crux idea here is, instead of building a neural network from scratch, can I reuse existing models trained on different data sets? So can I transfer my learnings? Can I transfer my learnings and the model that I learned on one data set to a different data set, right? To solve a different task altogether. My task could be dogs versus cats. The ImageNet task is like you have thousands of categories and you're trying to detect whether an image has an object of a specific category or not. It's called transfer learning because you're taking the model that is trained on a different data set and you're transferring this knowledge to solve a completely different task, right? So let's say multiple cases here. Okay, there are multiple cases and there is some practical advice that is very good. So let's take case one. Okay, case one here is that we can use, right? Let's take VGG16 as a sample, right? So VGG16, if you look at the architecture, right, this is one way of looking at the VGG16 architecture. You have convolution blocks, you have second convolution, again third bunch of convolutions, etc. What you have just before the flatten layer, look at this, at the end of this layer, what you have here, just before the flatten, right? So here, as soon as you flatten, what do you get? You get basically an array of features, right? You get basically a linear array, right? At the time of flattening. So these features are called bottleneck features. So what you can do for your task is this. Okay. So the first way is you can use a pre-trained model. Okay. So let's assume I'm using a pre-trained model on ImageNet. What I can do is, imagine if I'm given a data set D, okay, of Xi's and Yi's. Let's assume these are images of cats and dogs, and my YI is basically cat or dog. It's a two-class classifier, cat or dog, right? These are actually images. So what I can do here is I can take my VGG network. Okay, this is my VGG network, right? I can input each of my Xi's, each of my dog and cat images. And instead of running the whole network, I can run the network only till the flatten layer, right? So what I'm doing here is, instead of learning the whole network, I will remove the last dense connected layers. I'll remove these layers. what I get here at the end of this, just at flatten layer, what I get is a big vector. So what I'll do here is I'll reuse VGG, but I'll skip the last dense connected areas. These are all convolution layers. You have lots of convolution layers. So I'll take the output. So I'll input xi. At the end of this, I'll get a vector here. What do I get here? I get a vector. I take this vector. I will use this vector. Let's call this vector as xi dash. Okay, my xi is the image from my original data set. My xi dash is the vector that I got by using the bottleneck feature. So these features are called bottleneck feature just before the flatten, right? So I will actually flatten them. Now what do I get here? I get a d-dimensional vector. So for every image, my x1, x2, so on and so forth, xn in my data set D, I will compute the corresponding x1 dash, x2 dash, so on and so forth, xn dash, using the VGG network. See, here I'm using the VGG network except for the last few layers. Because look at what is happening actually in the VGG, right? The first convolutions are actually detecting edges. By the time I come here, I have a bunch of edges. By the time I come here, I have a groups of edges, right? So probably by the time I come here, by the time I come to my flatten layer, right, my bottleneck features here contain a vector representation of my image, which could say, I'm not saying it exactly does this image contain a circle like this? Does this image contain a triangle like this? Or does this image contain a cat-like face? Okay, I don't know how to draw cat face as well. Does it contain a tail? Does this have 4 legs? Okay, so you could get a representation like this where it is high when there is a tail, right? Because you're doing object recognition everything already, right? This whole network was trained for object recognition. Remember, ImageNet has tons of images of cats and dogs, right? So what you're doing here is you're reusing the VGGNet, but instead of using the whole network, you're using all the convolution layers. So you're using VGGNet as a feature engineering tool. And the dense vector that you get here is called a CNN code. Because what is it doing? We are using the convolution layers of the VGG network to actually convert an image into a vector, into a code. And now I have my x1 dash, x2 dash, x3 dash. I have this new data set. Let's call this data set D dash. Correspondingly, I have my y1, y2, y3, etc. On this data, I'll train a simple model. Okay, because I have a 2-class classifier, I can train a simple linear model like a logistic regression. Okay, this is case 1. Okay, so in case 1, what are we doing? We are using the bottleneck features. Just before the flatten layer or at the flatten layer. And we are using the pre-trained model of VGG16 plus ImageNet as a feature engineering tool to create CNN codes. So we are reusing the model that exists, and this model has been trained on ImageNet, but we are reusing it as a feature engineering tool. Okay, that is case 1. Okay, case 2. Let's look at case 2. Case 2, right? What other thing that I can do here is I have my CNN. I have my VGG network, right? So I'll show you another example. So what I can do here is I have multiple layers of convolutions, right, in my VGG16. So I have a model which is VGG16 plus, which is trained on ImageNet. I already have this model in Keras. Okay, and I have my new data set D, which is basically images xi and yi. Okay, remember the last few layers, okay, because the last layer in VGG network, when I'm especially solving for ImageNet problem, is a 1000 class softmax, right? So what I'll do here is, because my earlier models, see, whichever image is there, right, it will still have edges. Edges are still important in images, right? Edges are still, at this stage, probably my model probably detects only edges. At this stage, it detects some simple shapes, right? And that is common between all visual tasks, whether you want to do a dog versus cat model or you want to do a 1000 class classifier, right? For both of them, edges are important, simple object shapes are important. So in case 2, what we will do here is we will take the original data set, And we will take the original model that has already been trained on ImageNet, but we'll do one thing. What we'll do is we'll freeze a bunch of layers. So these are all the initial layers, right? Sorry. So all the initial layers that we have, like this, all these initial layers, we will simply freeze them. What do I mean by freeze them? By freeze, I mean, I'll say that the weights and kernels in these layers do not change. They're constants. Okay, I'll just make them as constants. By freezing, what do I mean? All the kernels, all the weights, and all the parameters, I just freeze them, or I make them constants. I will only modify the last layers of the network. Okay, because the early layers, remember, the early layers or the starting layers detect very commonplace things like edges and simple shapes. Why bother about them? Because that is common between any task. Whether you want to do dog versus cat or 1000 class classifier, the edges are still very important and shapes are still very important. So what if I freeze all the early layers and I just modify the last two layers? So the way I will actually do this is this. I'll take my dataset XIYI. Right? I will train this whole network by not changing. I'll make the weights and everything here constants. I'll only make the weights that are here and here as variables. And I might change the last softmax layer. Instead of a 1000 class softmax, because I have a cats versus dogs, I'll do a 2 class softmax, which is nothing but logistic layer, a simple logistic regression. I'll make these small changes, and I'll make only weights in these layers, the weights and kernels only in these layers as changeable. So when I do backpropagation, I'll only backpropagate weights only through layers which are very close to the result, output, right? I'll make rest of these things as all constants. So what are we doing here? So in case 2, right, we are only fine tuning the last layers of the neural network using the new dataset D. Okay, and the fine tuning is done on what does this neural network mean? This neural network is already trained on VGG plus ImageNet. This is a VGG neural network trained on ImageNet data, and I'm just fine tuning the weights. And one thing you have to note is when you fine tune, you should ensure that your learning rate is small, right? So that your weights don't change too drastically. Okay, that's something that you be careful about. There is a third case that you can do. The third case here is, instead of retraining just the last few layers, right? You have the model with VGG16 plus ImageNet, right? You can use this as the initial model. And you can change the whole model. You can tune the complete model. Using your dataset D of Xi's and Yi's. Right? So what are you doing here? You're using the final output that you got on VGG plus ImageNet as the initialization for the new model, and you fine tune it. When you fine tune it, of course, you keep a low learning rate. Just keep a small learning rate. But you're fine tuning all the layers. You're fine tuning the whole model here. Right? That's a third option. We'll see when to use what option. The first option is don't fine tune anything. Just use CNN codes, use the ConvNet as a feature engineer. Second is just fine tune the last layers. The third option is use the VGG plus ImageNet as the initialization, and then fine tune the whole complete model using the new dataset. Okay, of course, there is always case 4, which is just ignore pre-existing models, retrain the network from scratch. And most people don't do this because this is very expensive. Because you have somebody who has taken weeks together on some of the world's most advanced GPUs and trained a whole model for you. Why dump everything, right? Because at the end of the day, simple things like edges and simple shapes are still critical for all object recognition tasks, right? So why dump everything? This is something that very, very few times you end up doing. And let's look at cases when we should do case 1, case 2, case 3, case 4. Right? I would argue that you should avoid case 4 most of the times, right? So Let's see where case 1, which is basically using VGGNet as a feature engineering tool. In the second case, you're just fine tuning the last layers. The third case, you're using VGG16 plus ImageNet as initialization, and you're fine tuning the complete model. In case 4, you're training everything from scratch. So it depends a lot on two things. So you have a new data set D, right? You have your data set for your task, right? And you have the original data set, which is the ImageNet data set on which the model, let's say VGG16 was trained. Which option should you take? Case 1, case 2, case 3, case 4 depends on the size of D. It depends on size of D. This is basically the size of your data set, the size of your task data set, right? And how different is your data set to the ImageNet data set? Okay, again, let's write cases. Case 1, right? Case 1. If your new data set D, right, is very similar to the original data set, which is ImageNet, right? And size of D is small, then you should not worry too much. You should just use the CNN codes, which is case 1, which means use a model like VGG16 as a feature engineering tool, right? And once you get your features, just train a simple linear model. Just train a simple linear model. That's it. This is case 1. Okay, if your data set is small, let's say I just have maybe 2000 images. Okay, and I know that my cat versus dog data set, is very similar to the ImageNet data set, because ImageNet data set also has lots of images of cats and dogs. Of course, it has images of planes, buses, trucks, humans, etc. But still, this data set is very similar to this. Imagine if this data set is completely different to this. Imagine if my data set is some MRI scans of my brain, right, of human brains, not my brain specifically. If the original if the ImageNet data set doesn't have any brain scans, and your data set that you have is some brain scan data set, and you want to detect whether there's a tumor in a brain in the brain scans or not, then your data set is not similar to the ImageNet data set. We'll see what to do there. Right? This is case 1. So let's look at case 2. In case 2, let's assume the new data set is large, right? But the new data set is very similar to the original data set, which is your ImageNet data set. Then what you can do here is you can simply fine tune your model. You can simply fine tune the complete network. Why are we fine tuning the whole complete network and not just the last few layers? Because I have a lot of data. Here, and I can afford to fine tune my network. Right? I can afford to achieve this. I can afford to do, because my data set is large. That's why I'm fine tuning the whole complete network. And when we do it, we keep small learning rates. So we keep small learning rates. Right? This is an option that you can do. Imagine if D is medium sized. And D is very similar to my ImageNet data set. Okay, let's think of this as case 3. If this is the case, then I can just choose to fine tune the last few layers. Right? If the original data set is large, right, I can fine tune the complete neural network, right? Because I have lots of data. And imagine I also have extremely powerful GPUs. If you don't have GPUs, processing large amount of data is hard, right? So if you have medium-sized data, you might want to fine-tune just the last few layers. Okay, so let's go to a different case, which is, right? Let's go to a different case now. What if your data set is small? And your data set is not same as your ImageNet data set. Then what do you do? Very simple. You have your VGG architecture, right? Multiple layers, right? And let's assume this is your dense layer and this is your output. All these are convolutional layers. Layer 1, layer 2, layer 3, layer 4, layer 5, etc. Remember, this is very important. Your data set is small and it's very dissimilar from ImageNet. Then if what were we doing here? If the data set was medium sized or even small, look at this. If the data set is small, but it is similar to ImageNet, we are taking the CNN codes, which are almost at the last layer. Here, we will take all the outputs at an earlier layer, right? if my D is same as my ImageNet, okay, I'm taking the last layer data as a feature engineering step. But if D is dissimilar, D is not same as my ImageNet data. But still, imagine if I have an image data set, edge detectors and shape detectors are still useful. So I'll take the output that I get here and I'll simply flatten it. And I'll use this as features. Right? So this is another hack. Especially this is very useful when your data set is dissimilar to the original data set on which the model was trained. And your data set is small. Since your data set is small, you can't train a full-fledged network. What do? You leverage the network partially, because this layer might just do edge detection, this layer might do shape detection. So why throw it out? Take one of the earlier layers, the output here, and flatten it and use it as feature engineering. So just dump everything else here. Okay, so use the initial layers as your feature engineering to create again some CNN-like codes. Of course, this CNN code layer, the CNN codes are very different from the CNN codes that you get when you have all of the layers except the dense layer. Right? There is a case 5. Right? There is a fifth case, which is your data set is large, right? And it is different. Your data set is different from ImageNet. Now, because your data set is large, you can train a whole model. So in this case, the suggestion here is, the practical suggestion is, initialize the model using your, let's say, VGG16 that is trained on ImageNet. Use this as the initial model. Okay, then you can fine tune the whole network, tune the complete network, because you have lots of data. Okay, and using the VGG plus ImageNet features, even though the data set is not same, using them as an initializer certainly helps, because this model is well trained to start with. The whole VGG model is well trained, right? You just fine tune the whole network because your data set is large. Right? All these are multiple cases that are very, very important. Actually, there is a very nice blog written for the CS231N course that is taught at Stanford. And this blog explains all of these cases in lots of detail. Right? What I've shown here is basically inspired from this blog. All the practical advice, everything. There's a lot of nice references also. So I'll provide a reference link to this blog in the description section of this video. But these cases are important to remember for transfer learning. And that it's very commonsensical. They're not rocket science, right? And if you want to read about these cases, there is always this very nice blog, which I have learned a lot from personally.